All right, so we were discussing on techniques for converting or representing data in different ways, and the two that we're considering today are going from UML to a relational schema and vice versa, from relational schema to UML. Okay? And so right now we're just considering the simplest of examples, right? Where at most you have one-to-many or one-to-ones or one-to-optional. But certainly there's other representations such as associations or many-to-many or an aggregation and a composition that we'll take a look a little later. But nevertheless, it's a UML seems to be one of the proper ways to get started on any data modeling endeavor, right? Where certainly it's a much easier way to communicate across any final representation that you might care for. Certainly, it's visual. It's easy to communicate with other folks that come from different backgrounds, and it's easier to get to start here. Even if you have to modify a data model that already exists, it's easy to first convert it into UML, do the conversion there, and then reconvert it back into a lower level representation. So today, so for the first couple of weeks, we're going to be doing UML to relational database. We're going to do focus on relational database for almost half the course, and then we'll transition to alternative representations such as object data models using Java, XML, non-relational databases, and other ways and challenges that go with using other ways to represent data. So let's look at now. So we looked at how to go from relational schemas to UML. Now let's look at going the other way around, going from class diagrams to relational schemas, and which is going to be your second assignment. We'll focus on this, where you're given a set of tables. Giving a set of classes, you will create a table for each one of those classes. And the fields would be the same attributes, right? You would take the same attribute that you have in a class and add them to the fields. And taking every single association that you have, any single relationship that you have, depending on whether it's weak, strong, or weak, or whatnot, you would add the primary keys and foreign keys that were not there to begin with, right? The associations were there, and the implementation of foreign keys and primary keys were implicit, right? So if there's no natural key that you could use as a primary key, meaning maybe you don't have an email, maybe you don't have any, you would create an artificial one, like a social security number or like any UID, right? All those are artificial primary keys. You would add them. So you would start from this transformation, from this UML class diagrams, and you will end up with this resulting schema, right? Where we have added all the artificial primary keys, right, and also the foreign keys that are referencing the implementing the relationships. Okay. Now we could keep going and simplify some of this, and we will notice that there are some natural keys that we could use instead of the artificial ones. Right. So if we can guarantee that the department names are going to be unique, then that would be a natural key that we could use instead of an artificial one. Right? So we could go on through each one of the schema, right, and decide whether we can do these shortcuts, right? So for instance, having replaced having removed the department ID, the artificial key, and now it's the name of the department. We can now use the name of the department instead of the foreign key being some arbitrary number. You could now have the name of the department can be the foreign key, right? So we keep going. If some relationships are one-to-one, right? We could certainly abbreviate the relationship so So we don't. So since the foreign key is going to be referring to exactly one student, there's really no need to have an artificial primary key, since the student ID will be one permit for one student. Right? So there's no need to have this artificial one. We can just use the student ID also as a foreign key, both as a primary key and as a foreign key, referring to that one student. Right? Also, if we know that one student is not going to be enrolled in a section multiple times, right? There's no real need to have a primary key for the enrollment table. We can instead create a composite key between two foreign keys, right? We know that the combination of student ID and section ID has to be unique, okay? So we could combine them and make that our primary key. The primary key is the unique combination of student ID and section ID without the need of having this artificial primary key. Okay? A couple other things, if we can agree that the title of the course will be unique, CS 5610 and 5200 and whatnot, and the name of the title. Then again, we can do the same thing. We could just remove the artificial primary key and just use the title of the course instead. Same thing, since we've removed the department ID, it's no longer we're using the artificial key. Instead, we're using the unique name for the department. We can replace the foreign key to use the name of the department instead. Same thing for the section. No longer do we need to use the course ID, the artificial one. Instead, we can use the title of the course as our foreign key that refers to the course. So you would go on and create these, make these changes to better represent the data that you have and not keep track of unnecessary artificial keys or values. Obviously, there's some limitations of the many-to-many, right, or one-to-one, that would need to be reify those things, right, where we have multiple departments to multiple students. The algorithm doesn't take care of that, right? We need to add a mapping table in between with multiple foreign keys referencing the original ones, but we don't have that. We'll take a look at this a little later. So some just good practices and good design for diagrams is first create the requirement specification. The requirements will drive the rest of the design. If the requirements are different requirements, then it's a different data model. Okay. Part of the requirements will be the kind of questions you would like for your data model to be able to answer. Right. We saw earlier that our first data model that we had for the track and the CDs, even though it looked fairly intuitive, right, that it would be able to capture the data, we realized that as we looked at some of the requirements of the things that we would like to be able to ask or be able to represent, our data model didn't support it. Right. So certainly you don't design a data model in a vacuum. Right. It's certainly within the context of some requirements. What is it that you want to be able to, your data model to be able to answer? What kind of question you like to be able to answer? Typically from the requirements, you would come up with a very naive preliminary class diagram where you might make some wrong assumptions that perhaps all nouns are classes. You don't know any better, right? That you might not capture right away that maybe some nouns are not actually classes, but maybe attributes of other classes, right? They could be subsumed into more complex classes. But a good place to start is to be naive about it and just everything's a class, right? And as you refine it, right, as you go through several iterations and present it amongst your teammates, right? You might agree that maybe this is this is only single value. It makes no sense to have it as a class. It could be an attribute of some other class, right? And same thing. The verbs will the nouns are going to be the boxes, and the verbs are going to be the lines, basically, right? The nouns are going to be capturing in classes or attributes, and verbs give rise to the or capture as a relationship between the nouns, right? Any two nouns. Also, you look for redundancy, right? If you see that you can traverse the data model or data set from any one class to any other class, right? In multiple ways, right? If you have cycles, especially in your data model, those are clues that maybe there's some redundancy, right? But not all cycles are redundant, right? You have to be able to say, depending on the questions that you like to be able to answer, there might be a redundancy. But if you have a different question, maybe it's not a redundancy. Right? So the same cycle might be redundant if you have one set of questions, but it might not be redundant for a different set of questions. Yes. So redundancy is always based on what is it that you're trying to ask, because when you start asking, you'll also come up with certain select statements, right? That are going to query your data model in different types of joins. Yes. And there might be different select statements that presumably are supposed to give you the same answer, right? But if you be able to answer the same question with two select statements, then certainly there might be a risk of redundancy there. And we'll talk about that a little later when we talk about joins and whatnot. Some inadequate relationships, you might find out that you oversimplified the class diagram, right? Making some assumptions that perhaps when you were reading it, you were only considering one noun with another noun, and perhaps it was a verb phrase that actually was referring to actions on 2, 3, or even 4 different nouns, right? That somehow 4 nouns are related to each other, not just 2, right? So those kind of inadequacies, you would have to try and identify them, and see that perhaps there are multiple nouns that are related to one another. You're going to go back and forth between weak and strong relationships, between one and one and many to many, and see which and decide which attributes are too trivial to be their own class, or could they be subsumed into higher classes. And this will iterate multiple times. As you go through it multiple times, you'll refine your data model. So ideally, in your assignment, you will start with a trivial, naive first approximation of the class diagram, right? And then show and document, several steps of iterating over this, right? And your train of thought as you decided on a first approximation of your class diagram, and several, and going through 2 or 3 iterations. Why do you decide to have certain attributes become classes, some classes become attributes, and where you might have found some redundancy or not? Yes? Right? I like to be able to see that train of thought. Okay. Right. So requirements analysis, we talked about this a little bit. It's a first phase of interviewing your users and looking at the existing databases, looking at all the forms folks are filling out, what kind of screens they're filling out, and just kind of the different reports that the VPs want, right? That the sales folks want, that the business owners. What kind of reports are they looking at? What kind of aggregations are they looking at? Right? Those are going to give us clues of what kind of, how do we best organize the data? What kind of select statements do we want to have? What indices do they need to optimize the queries to better perform for the particular reports that these folks need, right? This will result in a requirement specification. So here's an example of this university example that we're going to be using throughout. Here's a university, and as we're listening and we're jotting down, in these interviews, oftentimes the client is going to ramble on, and a lot of it is going to be irrelevant, right, to what is it they're trying to achieve, right? And it is our responsibility to kind of try and lead the conversation and identify what is irrelevant and what's relevant, right? They might spend some time explaining things that have absolutely no bearings on what it is that we're trying to achieve. So here's an example. So the university is composed of departments. Academic departments such as mathematics and drama departments are responsible for offering courses. Non-academic departments such as admission and the dining hall departments are responsible for the other tasks that keep up the university running. Probably that's completely irrelevant, right? That we're not keeping track of human resources and dining halls and any of that, right? Probably we're not even going to data model any of that, right? Nevertheless, it's very, very common that that our clients will give us lots and lots of irrelevant information. It is our task to sift through that, right? Each student in the university has a graduation year, majors in a particular department. In a particular department, they could have said multiple departments, right? But it looks like it's a particular department. Each year, the students who have not yet graduated enroll in 0 or more courses. A course may not be offered in a given year, but if it is offered, it can have 1 or more sections. So this gives us clues about, okay, it could be not offered in a given year. So this kind of gives us clues it's 0 or more, or 1 or more, right? Maybe it's required to be every year. Over here it says that that if there is a course, then it can have 1 or more. It looks like it's required, right? If there's a course, there has to be a section, right? So at least there's a 1. It's not 0 or more. It's 1 or more. Each of which is taught by a professor. By a professor, right? It looks like it's just one professor that keeps track of this. A student enrolls in a particular section of each desired course. So each student is allowed to have 1 car on campus. In order to park on campus, the student must request a parking permit from the campus security department. To avoid misuse, a parking permit lists the license plate and model of the car, right? So that also gives us a clue of what it is that we're keeping track for the the kind of granularity that we want to model about the car, right? Looks like we don't care about the color. Looks like we don't care about the year and the model, just the model and the license plate. So here's some of the requirements and what kind of things we would like to use, some kind of use cases, perhaps. That be part of the requirements document. Allows students to declare and change major departments. So it looks like they can change the major. So they can modify the major. Right, that foreign key that references the department, they should be able to change that. Keep track of the parking permits. Allow departments at the beginning of each year to specify how many sections, courses, and whatnot. Right, who's going to be teaching that section? Currents to be able to enroll. Professors to assign grades to students in their sections, right? So here's some examples of what the use cases might be, and as part of the how the functional requirements would then be driven from these use cases. So a naive iteration over a naive reading of these requirements, right, might come up with this list of nouns and this list of verbs, right, and how they relate. Different nouns to amongst each other. So you have universities are somehow related to departments they're composed of, right? So offers, has, graduates, majors, enrolls, receives. So any one of these verbs seems to set a relationship between at least two nouns. At least 2 nouns, but it could be more than 2 nouns, right? As we see a little later, some of these, depending on how you interpret it, we should have considered not just 2 nouns, maybe 3 or even 4, right? And that changes the interpretation and the data model later on. So you have the list of nouns on one side, and you have the list of verbs on the other, and how they relate each one of the different nouns. Also, we need to consider what the scope, that box of the system that we're building. For instance, in the interview we keep repeating university here and there, right? Are we modeling the university? Should we keep track of the university? Maybe the address of the university, when it was founded, and things like that. Well, maybe not, right? Nowhere was it required that we keep track of any of that. And again, it depends on the scope, right? If you are the Department of Education, is there such a thing still? In the Department of Education, maybe you do want to keep track of a list of universities. Yes? So it would make sense that you do have a table where you list all the universities, right, and then all the courses, maybe, right. But if you are implementing something for a university, right, maybe it makes no sense to have a table of universities where there would be a single record of one university. It just makes no sense, right? So typically there wouldn't be a class university or a table university that you keep track of any of that information. Again, it depends on your scope, right? So many of these nouns would be irrelevant, right? Like campus and universities and maybe the car. Maybe you just want to keep track of the model. Maybe the license plate. In the license, for the permit, you just want to keep track of the license plate and the model, not an actual car, right? Perhaps that's enough to keep track of for the permit. Request, composed of. So a lot of these nouns and these verbs, might be as you iterate over this, you might find them to be irrelevant. And this would be apparent as you interview and discuss this with the stakeholders. In this case, would be me. So here's a preliminary class diagram that you might have come up with. Again, a naive first approximation of what the class diagram might be, right? And this I want to see this right in the assignments, right, where you first come up with a first approximation, and then you iterate this towards an ultimate design. So here we have the different nouns that we chose: students and departments, and grade, professor, section, whatnot, permits, car model, year, license plate, and then the various verbs. From deciding that goes from the from one direction. The student graduates in a year. Students are enrolled in a section. A professor teaches a section, right? Professor assigns a grade. A student receives a grade, right? And we might have chosen a particular set of cardinalities that you have. A student might have multiple grades. You might have multiple assignments. The professor assigns multiple grades to multiple students, right? So this is the first approximation, right? And as we iterate over this, we see that we start looking for adequacies, right? If this is actually capturing and answering some of our questions, or and also we're looking for redundancies. Can we answer certain questions, following multiple paths, right? So certainly these cycles are of concern, right? Students, grade, professor, sections, right? That you can iterate, that you can navigate from the student to the section in two different ways, right? From student enrollment or through the receives, grade, professor section, right? Or navigate to the sections from student, department, course to the section. So these cycles, right? We need to look carefully to that, whether we can navigate in both ways and answer the same questions following different paths. It might be that a particular question can only be answered following a particular path, even though there's a cycle, right? There's no way to answer the question following that cycle, right? If there's no question for that cycle, why is even the relationship there, right? Right. So right. So first, let's look at some inadequate relationships. Let's look at some what ifs, right? In particular, the phrase that we looked at earlier, where the student enrolls in a course, right? We might have interpreted and designed it this way, where we want to say students, courses, and sections. Right? Notice that the cardinalities seem to be okay, right? Notice that the students enrolls in multiple courses. That's many to many, so that makes sense. And also, we mentioned that a course has multiple sections, so the one to many, that also makes sense, right? But a closer inspection, we see that what some of the original questions that we were considering earlier, that we wanted to know, which student is enrolled in which section, right? This doesn't allow us to answer that question, right? Since here this section has references back to the course. But there's no way to relate the section to a particular student, right? We can have, given a section, we can know what particular course you're in, but there's no way to answer which particular student for that one. Since this is a many-to-many, one course might be related to multiple students, right? There's no way to tell you for a particular section which student is in a particular section, right? So again, it's because of the question, right? Tells us that this is inadequate. Can we answer the question given this model? And we might say, well, actually, maybe not. Right? This is not an adequate relationship. And then it says, okay, can we reshuffle this in such a way and perhaps decide on the actual representation that we chose was that we have a student relation related to multiple sections. But once you have a particular section, a particular student, once you fix the student, you know exactly what section they're in, so you can answer that kind of question. And once you know the section, you can then answer the question of what course for that particular section, by following this path, right? Which you would not be able to answer it had we chosen this path. Even though the cardinalities are okay, even though the relationships make sense, you're not able to answer. So whether it's inadequate or not is based on the kinds of questions you would like to answer. Right, so you want to exhaustively go through each path, answering the questions that kind of queries that you want to be able to answer. So let's look at a couple of other inadequate relationship. Receives. So this receives over here. Student receives grade, but there's no way to know what grade did you get. So the professor assigned this grade to the student, but we don't know for what course. For what course did you get that grade? So somehow we're missing a relationship between the section or the course, right? So somehow we're missing this. Or assigns, captures grades, professor gave, but no student to the section, right? And the reason we might have ran into this issue is that we might have oversimplified when we were reading the sentences, right? When we were reading, we just read student receives grades, right? But actually, it was part of a slightly more complicated sentence. It was a longer sentence, right? Student receives grades for an enrolled section, right? Right. So this is a verb phrase that actually relates three things, right? The student, the grades, and the section, right? So it's not a two-way relationship; it's a three-way relationship, right? The professor assigns grade actually was the professor assigns a grade to a student for a particular section, right? So again, it's a verb phrase that relates not just two nouns, but three or even four nouns, right? So this what we originally had considered of this multiple many-to-many relationship between student and grade, it's actually a little more involved in that it relates three things, right? Students, sections, and grade. But we know that this three-way relationship really doesn't have any way to actually implement it, even in UML, or maybe with an association would be a good place to go, right? But thinking about how we're actually going to be implementing it once we go to SQL, we can replace this verb. We can replace this verb with a noun, right? That can capture the relationship between the three, right? That can have a one-to-many with a grade assignment, right? The actual grade that you got, right, for a particular section. This says, given a student in a particular section, this is the grade they got. Right? So it creates those relationships. Eventually, obviously, this is going to be implemented with foreign keys going from the grade assignment, going back to the student, to the section, and then the grade. Right? Assuming that we have a kind of like a grade table, all possible grades will be listed there. A minus, B plus, B minus, and whatnot. Okay. Right. So this says, right, that if you give me a particular student, then I can give you all the sections that they're in, right? And for each one of the sections, like you're given one section, given a combination of student and section, there's only one grade possible grade that I have there. Right. Right. So notice that obviously we know we're gonna be end up, right. We already saw the result. Eventually, this is going to become the enrollment table, right. And that makes relationship between these three classes, and we can start thinking ahead on how is it that we're going to be implementing this, in the low-level implementation as relational data, the relational schema, right? We start thinking how we're going to reify this, how we're going to implement this in a concrete infrastructure. So here's one of the first major modifications that we're doing here. We're taking the grade, the section, and the student, and we are replacing it with this three-way or even four-way relationship with the professor. Right? So now we know who for a particular section was teaching that section and what grade they gave the particular student in that particular section. If we keep going a little further, we start seeing, we might go through several iterations where we might find several of these inadequacies, and then we start looking at are some of the questions could they be answered multiple ways, following multiple paths. So for instance, the question on retrieving all the section a student is enrolled in, right? It could be answered multiple ways. Through the grade assignment relationship between the grade assignment and the section. So the enrolls in relationship that we have here, the enrolls in over here, right? This enrollment relationship that you have between the student and the section, it could also be answered between the grade assignment, because this grade assignment already has a relationship over to the section, right? Meaning, given a student, I already have all the assignments that they're in, right? And this has foreign keys back to the section. So I could follow this, given a student, I know all the records that are associated to that one instance. And from here, I have one section per grade assignment that I have here. Right? So I could answer what sections I have given a student following this path. So this path of one to many to many is redundant. Right? So I would remove it. Otherwise, right. I would have to implement it. If I implement it, what would I have here? I would have another many-to-many here. Right? Because notice this many-to-many, I would have a map table here. This map table is exactly what I have here. It's already giving me that, right? So we remove that. Also, the professor assigning, because there's only one professor, right, for each section. Right, it's not necessary to have a reference to the professor. There's only one professor that could possibly be assigned to this section. If there would be multiple professors, then maybe we can keep it. Right? But since we only have one professor, there's really, if you give me the section, I already know who the professor is. Right? So I can know who assigned the grade because I know the section and I know the professor. There's no need to keep access or a foreign key to the professor. I already have a foreign key from this section over here to that professor. There's no need to go there that way. So we also remove that assigns. Now, not all cycles necessarily are redundant, right? And so here's a cycle, right? That you can navigate, like for instance, between the department and the students. You can either navigate from the department to the student, or you can navigate starting from the department, following the courses, following the sections, the grade assignment, and the student. But notice that both of them are answering two different questions, right? One of them says, given the department, give me a list of students, right? Which I can't answer following this other path, right? This one gives me you're giving a course, given the grade assignments, give me the students, right? But it cannot answer departments and students. So I do need that. I cannot drop that relationship there, right? Even though I could navigate this other way, right? Again, depends on the questions, right? Whether it's redundant or not. Majors is not redundant. So okay, so we have removed several of these associations. We identified that we needed an additional mapping table in between that related these three things, and that there was a redundancy between the professor and the assignment that we can add it to the section, and we also removed the relationship between students and section. So we've gone through these iterations. Let's go through a couple more. This So let's look at the departments, right? So in our original requirement, it was that one student can only choose one department, right? So we were, I think we were right to choose that it was a many to one relationship. That was okay. The requirements might have been that a student could actually choose multiple departments, right? Multiple majors. So it could have been a many to many, right? It could have been a weak relationship, or many to many, right? In that case, we would need to reify it, right? And any mappings that we might have like this, many to many, we would have to substitute it with something that can actually be implemented, like a mapping table that would have foreign keys to both. We already did that for the enrollment table, right? Which I think we call a grade assignment right now. So that we reified that it was associating three different classes, right? There was no physical way to actually implement that. Here we are doing it for the many to many in the department. This was not actually the requirement, but this is kind of like a what if, right? Would have been a many to many. We would have had to reify it. Also, we could have asked that if we had a many to many between the department and the student, we might have been asked to keep track of the majors, the GPA for each major, right? If it was just one major, you could have a GPA, and you could keep track of a particular GPA in a particular semester, or the overall for that particular department. Right? And if you add a many to many between the student and the department, this major GPA over here kind of loses its value because I don't know what the GPA is for a particular department because it's associated with the student. Right? So something that would have worked just fine if you just had one department, now all of a sudden it's not good enough, right? Obviously, we would need to reify this, obviously. But even if we reify it, right, we still wouldn't know, given the department, what is the GPA that is for that particular department. Right? So somehow we would need to move this GPA somewhere here that would keep track of the relationship between both the student and the department. Right? So moving that, it would become an association. It would be a UML association that again, this is fine to leave it as a UML class diagram, yes? But when you're going to reify and actually implement it in a relational schema, it needs to be replaced by a mapping table, right? That has references to all the other ones, which is pretty much what we did for the grades assignment, right? The grade assignment and the enrollment table, right? We reify that three-way relationship between all the three classes. Or it might be that the requirements might have been that students can decide to be undecided, right? I'm allowed to join the university, but I don't declare major, right? I declare at a later time, right? So again, the department now becomes optional, right? But it would be only one department. Now, if I have a major GPA, again, it would be optional. I don't know what it is, right? If there's no department, then I don't have a major GPA. But notice that this, because it's hanging off of this student over here, there's kind of no enforcement that if there's no department, I should not have a major GPA either. Right? There's no enforcement here, right? I could inadvertently not have a department and by mistake have a major GPA. Right? My data model is not enforcing that optionality. So instead, what we could do is, again, because now that's optional, we could bring this over here, right, and add additional data model that would enforce the fact that the whole thing should be optional. If you have a department, then you have a major GPA. If there is no department, then you shouldn't have a major GPA, right? You should all be behind an optionality. So again, the way we could achieve this is, again, to reify, put a mapping table in between that the whole thing is optional, right? If you either have a record that tells you what the department is and what the major GPA is, or you don't have a record and there is no department and there is no GPA either. Right? So this would enforce the optionality of both. Okay. Okay. So let's take a look at let's focus a little bit on this end of the spectrum of here with the permits, the license plate, and the car model, and whether if we decide things to be optional, this is the subset of that part of the UML diagram. Then we have an expiration date. Oh, okay. I think we're considering to see whether a permit might have an expiration date, perhaps if you're a student. So if you're a student, the permit is good for the semester or maybe the academic year. Instead, if you're a faculty and you're going to be here for many years, the permit doesn't expire. Right? So whereas the student would have to perhaps apply for it every year or every semester. So here we would like to be able to capture that optionality, right? Whether a student has a permit, if they receive it, then it has an expiration date or not, right? But if you don't receive, there is no expiration date. The whole thing is optional. Right. So here's a way that if you're a student, if you have an expiration date. If you're not a student, then you don't have an expiration date. Also, we might decide that the permit is only a means of getting a hold of the actual data that you want, the license plate and the car model, right? And we might decide that this one-to-one relationship is not worth keeping track of, right? We might decide by design that the permit could actually be part of just a student, right? Because it's a one-to-one. It could just be, instead of its own class, it could just be just a couple of fields in there, right? Since you're just going to have it for that particular student, right? And we could have the permit class just be subsumed inside of the student class, right? And then the student can then have foreign keys back to the car model and keep track of the license plate. Again, depending on how granular you want to represent cars. In this particular case, license plate is enough. Once we've subsumed some of these classes, we might keep going, right? And say, well, are there other classes that perhaps should be attributes, or vice versa, should be some attributes that should be classes? Like for instance, the year and the and some of the other nouns, like the classes and whatnot, could they be instead attributes, right? Like the license plate, could they be also attributes? Again, this depends on the domain, right? If you're a car company, maybe you do care about those details, right? Or so, for instance, like the professor, right? If we're only keeping track of the professor's username, and we're not keeping track of anything else like office hours and where their office is and whatnot, any grants or whatnot, then perhaps we could decide that doesn't need a class, right? A class would keep track of all the professors in the university, right? And then we would have foreign keys to these professors. But if we're only keeping track of the username, it's as if keeping track of the foreign key, right? So that's the only thing that we're keeping track of. So any class that we would convert into an attribute, that class might have relationships with other classes, right? Might have associations with other classes. So all those classes that were referring to this one class that's going to disappear, right? We need to replace those associations with actual values, right? Actual properties, actual attributes in those original classes, right? And then we will remove all the associations. So for instance, we're going to remove, for instance, the grade. We're going to remove the grade, and instead it's going to be subsumed inside of the enrollment table. Instead of the professor, that's also, since we're only going to keep track of the username, it's going to be subsumed into the section. Same thing with the year. The year Instead, it's going to be just an attribute of the section or an attribute of the student. Right? So any relationship that it has, right, needs to be subsumed into those classes. Same thing with car model and license, right? But they're going to just become part of the permit. Right. So having done that, you end up where we were presumably heading, right? The same 5 or 6 classes that we started off with, right? That was the original intent. Notice that some of the attributes here are somewhat missing, like the department name, the course title, and some. Obviously, there's many other attributes that were never mentioned in the original requirements. All of the things that were considered to be obvious, right, or assumed. That, for instance, the student doesn't have a first name, last name, username, right, things like that, or a password. Things like that are not in there. Again, course title is not in there. The department name is not in there. They were not in the original data model. You would go and take a look at what are the obvious attributes that were never mentioned but were implied. Right. So again, your knowledge of the domain might help you filling in those blanks, like a student name, the title for the course, or the department name. Right. So just like classes, right? Some of the attributes themselves might have multi-valued, right, represented as arrays or lists or sets or hash tables. Some of the attributes might also have multiple values that can be represented as arrays or lists. Those need to be converted as well. Aggregations, we don't have any aggregations. None of the life. We didn't cover any of the life cycle rules in the example, but nevertheless, here's some examples of aggregations where you might have a car that might have references to a particular engine or a particular set of wheels. That even if and you might be keeping track of all your wheel inventories, right, and all the inventory of all the engines for different cars, and orders. You're ordering different engines or ordering a car. If the order goes away, right, if you have a record with a particular engine that you're ordering, but then the order is canceled, notice that to represent that order, it has to have a reference to the engine that is being ordered, right? But if I remove the order, it doesn't mean that the engine gets removed, right? The record for so this is being represented as an aggregation, right? It's an order might contain one or more engines, right? But because I remove the parent, doesn't mean that the child is removed, right? Same thing with a car. You might have a record for a car that you're building, but if you cancel the creation of a car might have references of the engine that is going to go into that car or the wheels. Again, aggregation keeps track of what wheels go with what car and what engines go with what car, but you don't necessarily remove the records if you remove the parent. So you would use aggregation to keep track of that, right? So there's no delete cascade. There's no cascading in the removal of the records. Or there's pretty morbid. If a person is gone, then the legs and hands go as well. Some generalization and inheritance relationships. Some examples on those. You might have a base class person, right? That has all the things that are in common with different types of people, like students and professors. They all have a name and they all have age and date of birth, first name, last name, and a social security number. We all have to pay taxes. So one thing that perhaps not is not relevant for this assignment, for the next assignment, is implementing or that we never covered. We talked about converting a class diagram, right, into a relational model. It gets complicated when you're asked to implement a data model that has specialization and generalization, right? We've talked about that, so let's talk about that a little bit. So certainly you have 3 classes, 3 tables. That makes sense, right? And Now notice what we're doing here is that a professor here has an integer value for their office, but presumably it also has fields, a name and age. Right? If I create an instance of a professor, presumably it also inherits the fields name and age. For the student as well, right? If I create an instance of student, it has not only the grades field, but it also has name and age as well, correct? Well, how would you capture that in a relational model, right? Right. So presumably there's 3 tables, and in the person table, you would keep track of name and age, right? And the person ID. Notice that the way we're capturing here is that the professor table would only keep track of the office, but the if I want to recreate the instance of the professor from the database, I would need to grab the data for the professor here in the professor table, but I would have to somehow join it with the data of the name and the age for that professor. Yes? Right? So the way we're capturing that is that we're having the professor's ID also be a foreign key to the original person table. But there's a one-to-one relationship, right? You cannot have a professor record without having, right, the other record that keeps track of the other fields. Yes? Right, they're meant to be one and the same. So to implement generalization, right, the base class has a primary key, but then the derived ones, the derived tables, the derived classes, have foreign keys that are also primary keys that match the primary key of the base class, the base table. Does that make sense? Okay. Same thing with student. Students, since they're both inheriting from the same person, right, they would have a foreign key that is also a primary key that matches the person. So I guess what I mean to say is that this record cannot exist on its own. It has to have an accompanying person instance. Here's another example where you have a course, TAs. You have a TA that is also a student. Right? So you can have, so all students are students, obviously, but some students are TAs. So if you're TA, you're also a student. Right? So let's take a look at this. So you have faculty here as a table, right? Implemented in just on the faculty table. So that's trivial. Let's look at course. So course, notice that it has a many-to-many relationship between students, and also has a many-to-many with TAs over here. Yes, and the TA is a subclass of the student class. So let's take a look at that. So we have the course table is all by itself, right? Capturing the number and the name of the course. So no big deal here. Notice that the taught by references the faculty, right? So notice that you have a foreign key going from the course table over to the faculty table. So you have a foreign key here referencing the faculty. So that's expected, right? We've done that. That's taken care of the algorithms we've seen so far. But let's take a couple more. Let's look at the student. Student seems to be a base class that only has a name and a primary key. There it is, right? And then TA, and notice that the way we're going to implement it is that it's going to have a primary key, right, that is also a foreign key. See that? It has this ID, has exactly the same name. It is a primary key, but it's also a foreign key, right, that references the student ID. Okay? And notice that it says on cascade delete. See that? That means that if you remove the corresponding student, you also remove the TA. It would make no sense to keep track of the TA without the accompanying student. Right? They're meant to live together, live and die together. Right? These two records. Okay? Assigned and register. Notice that these relationships of registered and assigned, notice that they're many-to-many. Right? The only way to represent that in a relational schema is to reify this, right? And the way we reify it is that we convert the association, right, with a table, with a mapping table that has foreign keys to each one of the other two. So here we're going to implement this with an assigned table with foreign keys to course and foreign keys to TAs. And this is going to be implemented by a mapping table that goes with foreign keys to student and foreign keys to the course. Right. So implemented here, assigned and registered. Right. Again, each one with their own references that references the primary key, references the TAs, and references the course. And this one references the student and references the course. Okay. Another example where you have vehicles parked in a garage. Again, these are nouns, verbs, nouns, verbs. You're looking for these clues, right? And has an, right? Those are relationships that those are clearly foreign keys and primary keys. So you come up with something like this, with cars and boats having things that are in common with one another: power, owners, VIN number, but having special cases for the number of tires, and the boats have number of propellers and names, and a one-to-many with garage. And so these are subclasses of this superclass. So again, their primary keys are going to be foreign keys that go back to the vehicle. Now, this is not the only way of implementing inheritance. There's actually 3 or 4 different ways of implementing inheritance. One way is to flatten the whole thing, right? Instead of having boats and cars and vehicles, you just flatten it into one single table. Right? 3 classes, right, but one table. And that table has all the attributes, right? The VIN, the power, the owners, the number of tires, the number of propellers and names, right? All collapsed into a single table. Plus an additional field that tells it, what is it? What am I? Am I a boat? Am I a car? What am I? Right? And some fields, if I'm a boat, then I don't care about the number of tires. But if I'm a car, then I don't care about the number of propellers and names. So those would be null, right? So that would be a flattened implementation. There's a couple more we'll cover. This is referred to as the normalized implementation of generalization. Okay, the one where you flatten the whole thing into a single table is called the denormalized implementation. We'll take a look at them a little later. And why would you use one and why would you use the other? So this is the normalized implementation where you have cars and boats, both subclasses of vehicles, where the primary keys are also foreign keys referencing vehicles, right? Primary keys also referencing vehicles. Associations, where you might keep track of a history or the different where you want to describe a relationship, a many-to-many relationship. We like to be able to describe some of the more specific aspects of that relationship between a frequent flyer and a flight, and the mileage that you've accrued over time as you've flown. Again, the way we would implement it is that we would reify this and convert this into a table, right, that would keep track and have foreign keys back to the original ones. Right? But in UML, this is the way you would capture it. Frequent flyer miles having foreign keys and primary keys going out. The mileage credit having foreign keys going out. And association classes, right, that would capture those 2 things. All right, I'm going to leave it here.